This is an old analog scope that I picked up on eBay for, I think it was £15. This is an oscilloscope that has a CRT, which is this thing here. So it's a cathode ray tube, and it works by having an electron beam that's steered around. And normally you will have it sweeping across like this, and you'll plug a voltage in, and then it will go, the point will go up and down, so you can see the waveform of what you're trying to measure and use it for measuring things. But they also have, these old scopes always have, it's a bit knackered, they have an X-Y mode where you can plug in 2 channels, and the voltage in one controls the X, and the voltage on the other channel controls the Y. So it's like an Etch-a-Sketch, just move the point around. Now obviously moving it with my hands here, I can't move it very quickly, but you can see if I move it really fast, you can see it leaves a trail behind. You can see a line and a squeak. But if we have something controlling these voltages much faster, then we can draw shapes on the screen. And that's the idea behind vector games like Asteroids and Star Wars in the arcade. And there was a home console vector machine as well called a Vectrex. That's the principle that these things use, and they're really special. They have some amazing characteristics to the display that makes them quite unique. So I've always wanted to make my own. Well, I say make my own. Have an oscilloscope like this, and then make something to drive the scope so I can play games on it. Okay, this bit's going to be quite long and boring, so feel free to skip it if you're not interested in the boring technical details. This is what I'm planning to use to drive the oscilloscope. This is a Raspberry Pi Pico, and then we've got a couple of analog to digital converters to drive the X and Y voltages. There's another Pico down here that looks like it's dead. Just ignore that one. That's just used for debugging. And then here I've got a wonderful custom game controller. These are the 2 outputs, by the way, from the 2 DACs. So before I describe how this is going to work in software, let's talk a little bit about how vector arcade games work, how the vector graphics work in those kind of things. Well, normally they would use something called an analogue integrator for drawing the lines. So the digital part of the machine, the CPU, would set up where it wants the line to be, the X and Y position of where it wants the start of the line, and it would set up, typically set up the deltas, like the change in X and the change in Y that it wants. And it would feed those to something called an analog integrator, and then kick it off, and the integrator will then sweep the voltages in a straight line. So you get the nice line on the vector. Well, and also they have a third input as well as the X and the Y. They've got a third input for the brightness of the vector, because I think typically the analog integrators would operate at 1 speed, so they would always draw lines at a constant speed. Now, there's a couple of problems with that for me. First of all, my scope doesn't have an input for the brightness. All I've got is X and Y. I can only change the position of the beam. And secondly, I'm not very good with analog electronics, so I don't know how to build an integrator. So what I'm planning to do is, because I've got these two DACs that I've got are very, very high speed. So in theory, I can drive them at maybe 1 megahertz, which is pretty fast. And my idea, my plan is to use the CPU on here to do the integration digitally. So instead of having analog components to sweep the beam along a straight line, we'll use digital control to step the beam along a straight line, but in very fine increments so that it looks essentially the same. Now the Pico, the Raspberry Pi Pico, I think is the perfect microcontroller for this job. It's got 2 CPU cores and it has a DMA engine and it has something called PIO, which stands for Programmable I/O. So the plan is to use the first CPU core just to run the high-level code of a game, say, and that code is going to decide where it wants to draw the lines. So it's going to say, I want a line here, and draw it up to there, and then there, and there, and there. So it's going to just decide the coordinates of the lines, and also how bright it wants them to be. And then what I want the second CPU core to do is take those lines and break them up into very, very small steps and put them in a buffer. Put those steps in a buffer. It's going to be a FIFO buffer with lots and lots of coordinates in. Now then, we can use the DMA and the PIO to then squirt the data out of the buffer to the DACs. The PIO can read a single 32-bit value from a buffer, and I might have 2 12-bit values within there. And what it can do, the PIO can read one value, take the first 12 bits, send it to the first DAC, and then trigger the chip select for that DAC. Then it can take the next 12 bits, send it to the same pins and the same I/O pins, and then trigger the second DAC to read those. And it can do that with very careful timing and at very high speed. It's also worth mentioning that we can vary the brightness of any line by varying how quickly we scan the beam across it. So if we want to have a very bright line, then we scan the beam very, very slowly. Give the phosphor time to light up. But if we only want a very dim line, then we just move it quickly. And we can do this with the digital integration by just varying how many steps we divide a line up into. So because each step is being sent out in the same amount of time, if we go with big steps, then we'll move the beam quickly. If we go with small steps, then we'll move the beam slowly. So that's the idea. Right, so let's turn it on and see what we've got. And here's a little test pattern. It's just drawing lots of squares in a spiral shape. You can see how we're changing the intensity quite well. We've got the squares on the outside are quite bright, and then they get dimmer towards the center. It's not perfect. There are some little jiggles that I'm not quite sure where they're coming from, and some of the edges are not quite straight. But it's working quite well. I'm quite pleased. There are also these little speckles here, where I think the FIFO for the PIO units is being drained. The CPU is not able to fill the buffers up quickly enough in some situations where we've got lots of short, dim lines. And one thing that's interesting is normally on this kind of vector display like this, you'll get a little bright spot at all the vertices, and that's quite characteristic. And this is missing here in most of them because the CPU core 1 is just filling up a list of points to move the beam to, and it doesn't stop. So the PIO, when it's sending them out to the DACs, it doesn't need to stop at the end of the lines. Normally with an analog integrator, there'd be a little bit of setup time when you're setting it up for the start of each new vector. So during that setup time, even though it's very, very short, the beam is staying in one spot. And that's what gives you that kind of characteristic little bright spot between the vectors normally. So what else can we do? Well, as well as lines, we can do points. And again, we're just altering the brightness by adjusting how long we hold the beam in any one spot. So here it just moves the beam to where I want to draw a point, and it holds it there for as long as I want for the brightness. And if we can do lines and we can do points, then we could do games like this one, where you have to defend yourself from space rocks in space. Completely original game. I'll just resend it. Now the cool thing about vector displays that I really love, that's really hard to get across in a video like this, is just how bright the little points are for the bullets. It's really kind of HDR, and I don't think, even if I could make a HDR video, I don't think that would sell it either. I don't know how bright the points are, but they're kind of piercingly bright. They're really cool, and I love that about these displays. So what about raster? These are vector graphics. What about raster? What if we have a 1-bit display where we want to do some pixel graphics, and those pixels are on or off? Can we trace the beam across and make it move across where we have pixels, and then skip bits where we don't have pixels? Can we do that fast enough so that we can build up a raster image? Well, let's give it a go. Here we have another original game. This one is more like a raster game. It's not quite exactly like a raster. It does scan down the screen, but anywhere that's black, we basically just skip. So the beam only draws the little spans where the pixels are on. This is a 1-bit display, so the pixels are either on or off. So here we just need to make the beam trace across where the pixels are on, and then where the pixels are off, it skips. So it's not quite the same as a traditional raster display, where it will sweep across every line and vary the brightness as it's going. If we want to do grayscale raster, then we need to vary the speed of the beam as it's sweeping across. So here I've slowed down this raster beam so we can see it building up frames. I'll slow it down some more so we can see it sweeping across, and then slow it down even more so we can see it really kind of speeding up and slowing down as it's skipping across each line. So then if I let it speed up back to its full speed, we can see what it should be. So this is a 320 by 200 raster image, a grayscale image, and the text is vector. So we can mix vector and raster on the same display, which is pretty nice. And of course, if we can do still images, then we can do video as well. And I'm sorry. Not sorry. Thank you for watching.